Good morning, everybody. This is Ben Rosow here with Solid Applications. I see we have 6 of our registered attendees online here. I want to welcome you and thank you for taking the time to see this webinar regarding SOLIDWORKS Simulation. So I'm going to get started here and kind of walk through what we're going to talk about today, and then at the end we can open this up for some questions if you'd like, and we'll take it from there. So let me just minimize my meeting here and we'll get going. So I am Ben Rosow. I've been with Solid Applications for about a little over a year. I was with a SOLIDWORKS reseller in the United States for 11 years, and I've been using SOLIDWORKS mostly through the last 20 years, since 1998. So I've been with using SOLIDWORKS for a long time. And I am a certified lead application engineer. It's a very lofty sounding title, but it's the senior certification that you get from SOLIDWORKS if you've got a lot of certifications. So I've got a lot of, fingers in a lot of pies in SOLIDWORKS: electrical, PDM, simulation, flow simulation, et cetera, et cetera. So I've been around for a little bit, and I know from what I speak. I've done a lot of tech support cases, a lot of demos, and a lot of consulting with customers. So simulation is kind of my bag, and I really enjoy it. I think it's a terrific tool, and I hope you get a feel for why I like this tool so much. All right, let's move ahead now with the PowerPoint. This is going to be death by PowerPoint, so at the beginning, so I'll just walk through the first couple things. We're going to talk about today what the limitations are of linear static analysis. Now, the tool we're talking about is the SOLIDWORKS simulation that comes with SOLIDWORKS Premium. It's not exactly simulation standard. If you didn't have SOLIDWORKS Premium, like if you had the base level SOLIDWORKS package, you could also purchase simulation standard, which is the same simulation you get with SOLIDWORKS Premium, except it also includes the trend tracker and fatigue analysis. Now, fatigue is one of the modules also of SimPro, but they brought it into this SOLIDWORKS standard. But it's not. SOLIDWORKS standard it's almost the same set of functionality as what you get with SOLIDWORKS Sim Premium. So linear static analysis, we're going to talk about that, what the limitations are, so the realm we work in, what we can and can't do, what types of meshes we have, solids, shells, and beams, adding restraints and loads, or fixtures as you might call it. That's basically what we do when we run an analysis. Keeping it real, how to not over-restrain your model, because it's really seductive or very easy to say, well, I'm just going to restrain this face and that face and that face, and that may not be realistic. If you over-restrain your model, you're not going to get results, and you're certainly not going to get conservative results. So we want to go over a little bit of that, how we think. Special contact conditions, I'll just talk about that in brief. Getting the detail you need without overtaxing your computer. A lot of that revolves around making meshes that are not super fine and detailed, but only putting in the detail where you need it, and we have good control over that. Analyzing your stress plots, your displacement plots, and what we can do with those to make them look a little different, to make them show exactly the information we want to see, and some work with deformation plots also. So starting out on the limitations of linear and static analysis, first of all, we only do constant loading and restraints. In other words, the restraints and the loads that we use do not change over time. We don't have ramp up loads and ramp down loads, and one load for a few seconds and then another load for a few seconds. Now, you can do that in Simulation Premium, but we don't do that in plain old SOLIDWORKS simulation. So there are no changes over time, no impulse loads. Now, what that means is that the loads and the displacements will be applied, and the study is going to iterate until an equilibrium solution is reached. That's what we call convergence. That means the study solves and you get a result. Also, the linear portion of linear static analysis means we're using a linear stress-strain curve. Now, the picture on the right shows a stress-strain curve for what would be typical of a ductile material like a steel. And until it deforms plastically, meaning until it deforms to where it won't come back to its original shape, or bend, as we say, or breaks, it displaces in a linear curve, meaning it'll come back to its original shape, and the strain and the stress have a linear relationship, as you can see highlighted in the yellow area. Now we don't go with linear static analysis into this realm. Now the simulation tool will analyze along that straight line as if a material were linear, but we need to know if we exceed yield, we're not getting the result that reflects what the actual curve will be in the plastic region. So we're working strictly with linear stress strain curves, things that aren't breaking or quite coming close to breaking. We can tell if they're going to, but we can't tell exactly what's happening at that point. So it's elastic deformation only. That means deformation that goes along this yellow portion of the curve. All right. Small deformations, that's another assumption. And what small deformations means is that we don't have to recalculate what's called the stiffness matrix. All throughout the model, we mesh the model, we break it up into little tiny components, and we make the assumption that the stiffness is the same. The stiffness will change as material compresses or as material gets put under tension. So under tension, the stiffness will increase. Under compression, the stiffness will decrease. Under large deformations, that happens, and you can no longer make the assumption that the stiffness is the same everywhere. We're making the assumption that stiffness is the same everywhere, meaning small deformations. And the tool is able to flag it for you when you have large deformations. Doesn't mean that your study won't be able to run and give you accurate results, but you have to kind of know what you're doing there. All right, so we're making the assumption that the local strain at any local region is small. That means the change in length over the total length is much, much less than 1. Regarding meshing, we're just going to go over a couple of just an overview of what the meshing tool looks like. We do solid tetrahedral elements. Tetrahedral elements are basically triangular pyramids. Now, that doesn't necessarily mean they have straight edges, because with a high quality mesh, which we often use, the edges actually are curved. So that's a high quality mesh. But we do solid elements, and you can see what it looks like here in a quick and dirty picture of what the interior of a model looks like when it's meshed up. We do shell elements. That's for thin things, typically sheet metal or constant thickness thin items. And that is a way to get the detail you need and apply a thickness. It's kind of a calculation engine for the thickness, and it enables you to get a lot of detail without as many nodal points, without as many equations to solve. So it takes a lot of the load off of your computer's CPU. And then beam elements does a similar thing for beams. So basically it treats beams as stick figures, and it breaks the stick figures up into lengths. It knows about the cross-sectional profile. Is it an I-beam? Is it an L angle? Is it a piece of square tube? And it knows the properties like the modulus of elasticity of the material and the moments of inertia. So basically it again is a calculation engine that works with the beams, and the beams of course are all tied to each other with joints. And that's handled inside the program. So that said, I'm going to move on now to talking about restraints a little bit. We have a tremendously detailed set of restraints. It's a large set of restraints, and it works very well. The simplest one is fixed. You just fix something in place. You say you can't move. We have a lot of ways of using a reference geometry. Like in this particular picture, we're using a plane to define what direction we're going to restrain that surface that's colored orange. So we can use reference geometry of all different types. We can do prescribed displacements. You can tell something it's going to move 3 millimeters, and it's something that people don't do often enough. It's a very useful functionality. We have elastic supports. We do different types of contact sets, so components can be defined to not be able to penetrate each other. They can be bonded as if they're glued with an infinitely strong glue. They can be defined to just pass through each other and ignore each other. So we have a lot of good control over contact conditions. By the way, no penetration can also be run with or without friction. So that's another little wrinkle we're able to handle. We have many different kinds of connectors. We have bolt connectors. You can see pictures of bolt connectors in a sheet metal part here. Spring connectors, where you define the spring constant. Pin connectors, hinge connectors, bearing connectors, like I said, spring connectors, rigid connectors, and several more types of connectors. So what I'm going to do here is I'm going to move over to SOLIDWORKS, and I'm going to just begin to show you a little bit about what we're talking about here. So here's a model, and I'm going to kind of walk you through what we basically do with our studies. So to create any study in SOLIDWORKS Simulation, and this is I'm kind of giving you a very basic tutorial here. When you add in SOLIDWORKS Simulation, you'll find that on your add-ins over here. and you can add it in the on so that it starts up on when you start SolidWorks or just in the current session. You can also find it in your add-ins here. You can see SolidWorks Simulation is turned on. That gives us the SolidWorks ribbon in the toolbar. And in fact, I'll tell you that I don't use a whole lot of these icons all the time because everything can be pretty much done off of the right click on the study menu here on the left. So when you create a study, all you do is you go to New Study and you get presented with your options. Now, if all you have is SolidWorks Premium, you're going to have the option to do a static analysis. I've got Simulation Professional and Simulation Premium, so I have a lot of other types of studies I can create, but basically you create a little static study. So here's a study I've created. I've got several studies down here, and they show up in tabs at the bottom, similar to an Excel spreadsheet with different sheets in it. So one of the first things we work with, working top to bottom, there's a parts folder. Now this is an assembly. It's got several parts. These linear sliders, they're made out of aluminum, and you can see here that a material has been defined for them. Excuse me. And then we have this plate on top, and we have this little weldment made out of a tube and a couple of little pieces of plate, and that's made out of carbon steel. So any material that is defined in the SolidWorks model itself, and we can go here, we can find these guys. So if I look at the rod link part and I look at it, you can see it's made out of plain carbon steel. That will come over into your study. However, you don't have to use that. You can override it. So I could go in here onto this this part here, and I could say Edit Material, and I could go choose any other material I want. Now you'll notice when you look at the materials, you have properties like the elastic modulus, that's the stress strain ratio, the Poisson's ratio, which is a neck down property. So as you pull on something, it will neck down and get thinner. The density and the yield strength in red. These are the ones that are necessary for a SolidWorks simulation study. You can make any custom material you want by either making just a new material or copying a particular material, going into your custom databases. You can create a new category off the right click, and then you can go and put a material in there and simply paste it in there, and then you can customize it all you want, change all the properties. So when you have your material all defined for all your components, you get a green check on the folder. Also, if there are components that you don't wish to study that are in your model now, you don't actually have to make a special configuration with those components suppressed. You can simply right-click on something, and you can choose to exclude it from the analysis. All right. Moving on, connections. Now, most studies will default have a globally bonded contact, but if you want, you can go into your connections tool and you can create a contact set where you might define something to be bonded or no penetration or allow penetration. We have two really good special useful ones called shrink fit. Think about a hub and a rim where the rim is heated and the hub is cooled, but they actually would interfere before that. And you slip them over each other, and when everything gets back to normal temperature, they're under tension and compression with each other. So we do shrink fit. We also do virtual wall. Virtual wall is really useful if you want to have something bolted to a large monolithic component that isn't moving, and instead of modeling that component and then restraining it and having to mesh it and solve for it and all that, we just define a virtual wall on a plane, and then we would use foundation bolts to bolt something to that plane. So we have a lot of control over our contact sets, and like I said before, we can also handle friction, and we can also handle small gaps. So if you have a small gap in there, you can actually have two parts that are close to each other behave as if there is a material between them that won't sandwich or get compressed. Okay, that takes care of our connections. What about our fixtures? Well, you can see here that I've done a couple of restraints already, and I'm going to get to those in a moment. But the first thing I'm going to do, again, is just right-click on my fixtures folder. If you don't know what you're doing, you can use the Fixtures Advisor. My feeling is that these are pretty self-explanatory. Fixed geometry basically means you are holding still, you're not moving, nothing's happening to you, you're just fixed in space. It's the simplest kind of restraint to put in. It's also the one that's most, I would say, overused, because sometimes people will fix things that aren't really fixed. I think the other thing that's most overused in a SolidWorks simulation study that makes it real easy is a bonded contact. We just assume everything is bonded. If I wanted to get very literal about all my stresses, I might, let's say, make this slider have a no penetration contact with the plate and then put some bolt connectors in here. Now you can do a bonded contact study, you could do a bolt connector study, and if you don't see much difference, then go ahead and bond it. It'll solve faster. But just one of those things to think about when you're bonding. It's kind of, everybody's wish is, gee, this stuff is just glued together with an infinitely strong glue. It makes things really easy, but that may not always give you the most accurate stress output or deformation output. So you might want to think about some of the other things we have to offer, like a no penetration and then some bolt connectors. Back to the fixtures, right-click the fixtures. You have things like a roller slider. You could apply that to a face, and it will just slide on the planar face that was on this part. Fixed hinges. Fixed hinges are really useful. You can apply it to one or more components, and it will keep the axis of something cylindrical in place, but it will allow the component to rotate around it, just not slide along it. Elastic supports. This one is a lifesaver. You don't use it very often, but when you need an elastic support, imagine something mounted on plastic mounts on wood, or an engine mounted on a chassis with elastic mounts. You could actually simulate something like that without having to model the chassis or put anything in place of the chassis. Bearing fixtures, very, very useful if you really want to get an accurate picture of what happens, let's say inside of a cylindrical region like this when something is loaded. You can do a bearing fixture. Excellent, excellent functionality. Foundation bolts. Foundation bolts are when you're bolting something to that virtual wall that I mentioned earlier. Foundation bolt is a great kind of fixture. We also have advanced fixtures. Now, advanced fixtures enable you to do something like say, well, I want everything on this hole to stay on this cylindrical face. I want it to be able to move radially, but not move, not rotate. So you might put in rotation and put the number 0 in there, so it prevents it from rotating. But you might allow it to move radially, that sort of thing. So we have 3 different types of motion that we can prevent something from engaging in, and you get an actual little picture here that kind of gives you a cartoon of what it means. Circumferential restraint, axial restraint, and a radial restraint. So that just gives you an idea. These little tooltips help your brain to quickly pick out what these different types of restraints are. One of the other things you can do is you can activate something and put a non-zero value in there in which you're telling it you are going to rotate, or you are going to move along the axis, or you are going to expand a certain amount. So it's got quite a lot of control of it. If you use reference geometry, you can apply it to a face and then use some other face as a reference, like a plane. You could say, well, this guy can't move farther from a plane or something like that. So we have a lot of, the reference geometry is something we use all day long, all the time. Very deep functionality, very deep. Okay, so let's take a look here. Now, I talked about not over-restraining the model. What we're going to do here is we're going to imagine that these 2 holes are on a shaft and that these pillow block bearings here, pillow block, they're linear slide bearings are sitting on shafts. Okay, so that will prevent this thing from rotating forward as we put a load on these little holes here and pull it off to the left. So let's look at what was done. We don't want to just say, well, you can't move. We don't want to just simply say you're fixed. That would over-restrain it, would prevent us from actually loading up this beam here. So let's look at the kind of restraints we have. The first restraint, you'll notice when I click on it, it lights up the surfaces involved. I'm going to simply edit it and you'll see how it was created. So what we did is the 4 faces were selected. We chose on cylindrical faces as the kind of restraint. And then we said, you can't move radially. What that means is you are going to have the same distance from the axis, all right? But we're allowing them to rotate and we're allowing them to slide along the axis. Okay. Let's put that one in your back pocket. Now we'll edit this next one. This applies to these 2 holes down here. And let me edit this one. Right-click, edit the definition, and what do we see? We've also applied on cylindrical faces to those cylindrical surfaces, and again said you can't move radially. What that means is that it can't get larger or smaller, and it can't move off axis, but it's allowed to rotate, and it's allowed to slide along the axis. So if you think about it, the first one is preventing, because these guys can't move radially, it's preventing from motion to go along this direction. It's allowing motion to go this way. The second one, the second restraint at the bottom, is preventing the whole model from moving this way or up and down, at least around this point, so the model won't float away. But it does allow it to move axially, and it can rotate a little bit here. So we're allowing this guy to be totally totally loaded with the load that we're going to apply. And speaking of loads, let's take a look at our loads menu here. If you right-click on external loads, forces are applied very simply. You apply them to faces or edges or even vertexes, corners. You can apply them with a reference, so you could say a load perpendicular to a plane or perpendicular to a face or along a plane or a face. Very simple to apply them. You can also make loads vary if you want over distance. You can apply torques similarly. You can apply a pressure. One of the interesting things about pressure is you can apply pressure with an equation so that you could simulate water in a tank pushing on the walls of that tank. That's a very easy thing to do. Gravity. Gravity, all you do is you give it a direction and you give it a value. Gravity works like crazy. It's beautiful. A centrifugal load. This will give you the loads that you would have if the model were spinning at a certain speed. You need an axis to define it. And so if you have something like a turbine blade, it's a great way to load it up with the centrifugal load it would have as a result of spinning. It doesn't physically spin the model, but it will give you the same loading it would have as if it were spinning. Bearing loads, they require a direction. Again, you can apply the load with a parabolic or a sinusoidal distribution across the cylindrical surface of the bearing. Temperature load. Now what a temperature load does is a temperature load will apply a single temperature to the entire body of the part, and it will apply it relative to a reference temperature. Let's say room temperature, and you want to study what happens when something is heated up to a certain temperature in an oven. You can also bring in temperature loads from a SOLIDWORKS Simulation Professional heat transfer study. You can import those. So if you have an actual temperature distribution, you can bring that into. Now, under loads, we have a prescribed displacement. It's really a kind of a fixture. Excuse me there. But it is when you want to apply a particular displacement. You say something is going to move 2 millimeters, and then you want to analyze, let's say, how much force was on that thing to make it move 2 millimeters. So instead of applying a force and editing that force and rerunning your study until you get a certain displacement, you just give it a prescribed displacement, and you can find out afterward what the reaction force is. Okay, remote loads, remote masses. That is as if you, let's say, if you had an engine and you wanted to treat that engine just as a weight to apply to the engine mounts, you'd simply give it a coordinate and apply it to the faces of the engine mounts and tell it how much it weighs. Same thing with if it were a remote mass, you'd apply gravity to the model and tell something how much it weighs and get rid of the model, so you don't have to actually analyze the entire engine itself. Same thing with the distributed mass. So we have a lot of different types of loads here. Let's go look at the really simple load we applied to this model. I'm going to edit this load, edit the definition. It was applied to these two faces, and it was applied based on plane 1 in the model, which is down here. And there are 3 directions you can apply it to: along the plane in one direction, along the plane in another direction, and normal to that plane or perpendicular to it. So if we look at this one, you can see that the little arrows are pointing to the left. So we chose along the plane in one direction, and they're pointing to the left, and we gave it 750 pounds. Now, if you don't know, have a feel for what that means, you can always go in there and change it to SI units, and it'll tell you that it's 3,336 newtons. So that's how what we're loading this model up with. Okay, now let's think about meshing it. The next thing we have to do, moving down one thing at a time, we're going to mesh the model. Now, when you mesh the model, it breaks it up into little tiny elements. So one of the things you sometimes need to do is you need more detail. Now, when you mesh it, you can mesh it coarsely, you can mesh it more fine. When you mesh it fine, you have more elements. The study takes longer to run. One of the things we have control of is mesh controls. Mesh control enables you to simply pick a certain region and say, well, I'm really concerned about the stress right around this face and this face. So you simply pick those faces, and you create that mesh, and you say, no, we want that mesh control to be really, really fine. Let's put that in millimeters, something like, I don't know, 2 millimeters of mesh size. And it will give you a fine mesh right in that region, and then the mesh will expand out to the default size you have in your entire model. So let's just take a look at the mesh that we have in here, and you'll notice that we have a fine mesh right down here, and that mesh expands out to a larger size. So on a big area like this planar surface here, we don't need a really detailed mesh, but we need more detail around here because we want to make sure we don't have any stresses jumping around from element to element. So you have very good control over making your mesh really fine where you need it without loading yourself down with a tremendously heavy model, meaning a large study. Let me look at the details. I'm very fond of looking at mesh details, and this will give me an idea of how big my mesh actually is. So here you can see that my maximum element size is about 0.3 inches. That would be something like on the order of 6, 7, 8 millimeters. Minimum element size. Now look here, we have 134,000 elements. Those are the tetrahedral elements, and we have 216,000 nodes. Those are the little corners of each element, and we have a high quality mesh, which means along each edge, let's say along this edge, there's another node somewhere in there. Right along here, along this edge, there's a node somewhere in there. So if you do a draft quality mesh, which does not have nodes in between, you would have a fewer number of nodes, but the same number of elements. Another thing this tells us is what the maximum aspect ratio is. Do I have long, skinny elements, or are they elements pretty chunky? That's a really good number there. You want to generally keep that number under 20. That's just kind of a rule of thumb. It's not an absolute rule. But if there's a particular area in your model where you're concerned about how rapidly the stress is changing across a small distance, you might want to look for areas in your mesh where you have very long, skinny elements. So one of the things you can do with a mesh is you can actually make a mesh quality plot that shows your aspect ratios. And that plot will be able to show you where your high aspect ratio elements are. If I go into my chart options, I can actually give me a maximum flag, and we can see, oh, it's right there, right in there. That's where the worst case is, and it's probably underneath one of these guys. There we go, right there. So we're seeing there an area where we have a high aspect ratio. All right, now this will give you a good picture of what your mesh looks like before you ever run a study. So I find that, if I'm ever running any difficulties, it's a really good tool to be able to make a mesh plot like that. Now, the next thing I would do in this study, having set it up like this, is typically I'll go and save the model, and then I would go and run it. Easy way to run it, right-click the study itself and hit run. Before I do that, let me just go in here and look at my study properties. You have control over a number of things. Do you want to use the large displacement flag? That actually changes the type of study and borrows from nonlinear functionality to redistribute the stress matrix. I'm not going to get into too much detail there. We won't need it in this case. If you have a model that is not really well restrained but doesn't have any residual forces on it, you might want to use soft springs to stabilize the model. You can get into adaptive meshing, which I think is kind of an out-of-date functionality but still supported. We really don't need that anymore. And you could bring in, let's say, results from a thermal study or from SOLIDWORKS flow simulation if you wanted. You can also control what solver we want to use. More often these days I use automatic solver selection, but if I uncheck that, you'll see we have several different solvers to use that give us different advantages. So just want to bring that up and want you to know that we have a lot of solvers to choose from, and the solvers that get added to the tool every year get better and better and faster and faster. All right, so now what I would do is I would run the study. Although I just did run it, let me look at my results folder down here and get my solver messages, and it'll tell me how long it took to run the study. Whoa, this was a bad one. It took 9 seconds. Well, let's take a look at our results here. All right, there's my stress plot. So we can see that we have 114 megapascals. That's well below any of our yield stresses. I'm going to animate this model and take a look at it here, and you can see that we're getting a little picture of what it looks like, a little cartoon. And this is not just done for the boardroom. This is done to actually give us a really good picture of qualitatively what's happening. So you can see that our stress plot looks like that. Now, right now, this deformation scale, this is multiplied by a factor of about 300. So it's not going to really move this much. It's just exaggerated for the purposes of making it plain. Let's take a quick look at the displacement plot. Looks like that. This gives you in millimeters what the displacement is, red being more displacement, blue being less. We have a lot of other things we can do. We have strain plots and things like that. And lastly, I'm just going to show you a quick and dirty factor of safety plot that I've topped out at a factor of safety of 20. So anything that has a factor of safety greater than 20 is going to be in the blue region. And here you can have a detailed picture of what the factor of safety looks like. In this case, we're in good shape. Worst case, the factor of safety is just under 2. Okay. One other thing I wanted to show you is that the model is interactive regarding making design changes. So what I've done here is I've got another configuration where I took the thickness of my tube and I changed it, and I took the thickness of these two tabs down here and I changed that. And what that is, it's in the other study. So you can just change your study, change your configuration. I've got a different configuration where now this guy is thinner and this guy is thinner, and we can simply look at the results we get there and take a look at the stress plot, and you'll see here that the stress has gone from maximum stress from 114 to 152, that we still are well within a reasonable factor of safety if all we're concerned about is plastic deformation. We're at 1.45, worst case. So that just gives you an idea, a very quick and dirty picture of the fact that SOLIDWORKS simulation responds to changes in your model. Now let me move ahead to another model here. This is a actual sheet metal model, a sheet metal tray. And when you create a study in sheet metal, it comes in by default treated as a shell. And you'll notice that SOLIDWORKS sheet metal will automatically give it the thickness that it was modeled with. Now, if you want to, you can override that and treat it as a solid. You can always do that. Okay. So let's take a look at what we did with this. First of all, the mesh, when you do a shell mesh, it looks like this. You've got a bottom side in orange and a top side over here. Looking real quickly, what we've got a set of bolt connectors, and they were foundation bolts, and we created a virtual wall at the bottom of this thing because I actually wanted to study, will this thing lift up? And just to keep time short here, you can see that I've applied a load on this edge here going sideways and going up, and I've applied a load, that's this load here, and I've applied a load on this edge pushing to the outside of the box. So if we're pushing in and up and if we're pushing out, we would expect some deformation accordingly. So let's take a look at this. This is our stress plot here. And it looks like that. Now I could animate that, but I think you've already seen what the cartoon looks like. Our maximum stress is 88 megapascals. Our material is 304 stainless steel, so we're well underneath the yield strength of 206. I want to show you a plot of the Y direction, that's up and down displacement. And this gives you an idea that, oh, my model did lift off here. All right, now what I've done is I've sectioned this model here because I wanted to be able to show that. So that's another thing you can see, that in this plot, I'm sectioning the plot along this edge, along this plane. So this is a really useful result to know that, you know, in this case, the virtual wall and the bolt connectors did a more accurate job than just simply taking the bottom of it and fixing it, right? Because we're actually getting some lifting going on in here, and if you don't restrain it properly, you wouldn't know that. Going back to the stress plot, you can see that we have a stress distribution that would be essentially no stress down here if we just put a plain old fixed restraint on there. All right, having done that, I will move on because we're kind of running out of time. I'm going to move on to beam elements. So this model has, this is a basic skid model. It was made as a weldment in SOLIDWORKS. And you'll notice that just like sheet metal comes in as shell mesh, a weldment comes in with beams by default. So we have beam elements coming in here. Again, you can take any one that you want. You can right-click it, and you can treat it as a solid if you'd like, just by right-clicking on it. So there, this reflects the cut list. We have a material that has been applied to this, in this case, A36 steel, which is commonly used for structural steel like this. We also have some solids, these gussets that are not beams, and they are bonded to the edges of the beams. And then we have this joint group. And the joint group has a joint wherever two beams come together. You can even see that I put in some cosmetic welds here. We also have a welding tool for SOLIDWORKS simulation. Let me hide the joint group, and I'm going to hide the loads just to show them quickly. I've loaded up these beams with a vertical load, and I've loaded up this joint right here with a sideways load. Okay, I've put some fixtures on the joints down near the bottom here at these corners, as if this thing is sitting on mounts, and I'm going to hide the loads and hide the fixtures. And now we'll go look at what the results are. There's my displacement plot. And you can see what the beams look like. Now, the beam plots can be shown with or without the actual beam profile. Now, I've kind of shown the beam profile here because, one, it's kind of sexy, and two, it gives you information about what's going on through the beam profile. So here you can see, as you look at the beam profile, you can see that it varies across the beam. Okay. We do a lot of other types of plots in beams, including bending moment. Let's take a look at bending in direction 2. Directions 1 and 2 are the long and the short directions. So there's your bending moment plot. We actually have a lot of bending moment going on right in there. We have a displacement plot just in the x direction. That just shows things in the direction that force was pushing. Again, we have an exaggerated plot. And then we also can do like a shear moment plot, which shows the beam bending moments, or excuse me, the shear moments across the lengths. Quite an interesting diagram. It's a lot of depth here and more than I can get into in great detail, but just to give you a little picture of what we can do here. So let's come back now to the our little PowerPoint and answer the question, well, so what? What have you seen so far? Well, what we've seen, it's a really intuitive tool to set up studies. I really firmly believe this. It doesn't take a lot of skinning of your knees to get functional with SOLIDWORKS simulation. We'd love to get you trained up in the tool, but you'll find that once you start using it, you're going to really like it. It's got very deep functionality. We don't just have a few simple restraints. We have restraints that have been developed over the course of 25, 30 years that have become very, very deep and functional. It's native to SOLIDWORKS, and what that means is interactive with the model. You saw that when I changed some geometry. You can run a simple study like that. You can do as many configurations as you want, change a dimension, mesh and run your study, simple as pie. Big league meshing capability. 3 different meshers, high quality, draft quality mesh elements, very accurate meshing tool, very robust meshing tool, fast mesher. It's got the industry's fastest solver. Our models solve really fast. The days of 5-6 hour studies, unless something is absolutely enormous, those are pretty much over. Almost everything I do solves in 45 minutes or less. Most of the things, I'd say 90% of the models that I run studies on solve in under 2 minutes. You get to analyze before you prototype. So you can actually do several prototypes all within the course of maybe a day in simulation before you ever build a prototype. So you know where you're going with your model and with your design long before you get to the point of actually prototyping. That's a big deal. So what's in it for you? 1, you can be faster to market, fewer prototypes. You're going to make better designs. I can attest to this myself. I put out better designs because I have an FEA tool available to me that's easy, fast, and accurate. You can reduce mistakes. You make a design error, something you hadn't thought about. I mean, it's an actual fundamental error in your thinking. You're going to find out with this tool really quickly. You're going to be able to save money for that reason. This is obviously one of the biggest motivators. If you were to take this to your management, that's one of the things you want to bring to them. You're going to save money. You're going to earn the esteem and the admiration of your coworkers. They're all going to be impressed. You tell somebody how hard it was, it took 3 days to do. You don't have to tell them that you did it all in 3 hours. I'm going to put this out to questions. I'm going to unmute everybody and see if anybody has any questions for us. All right, folks. Well, that's all the questions we have. I'm going to sign off for today, and I wish you all well and happy FEA solving.